This is geometry lesson 6.2, isosceles triangles. The big idea says those triangles that are reflection symmetric, specifically the isosceles triangles, possess properties that scalene triangles do not possess. So quick review, isosceles triangles have at least two sides equal. They can have all three. That's called an equilateral triangle, but that is still isosceles. It's two or more. So basically, two or three equal sides is isosceles. And scalene means all the sides are different. Remember that the angles and the sides correlate. So if a scalene triangle has no equal sides, it means it has no equal angles. An isosceles triangle, if it has two equal sides, it has two equal angles, and a third one that's different. Or if it's an equilateral triangle, which again is isosceles still, but it has three equal sides, it's going to have three equal angles. And in that case, it will be 60, 60, 60 because you've got 180 degrees in a triangle. And if it's split three equal ways, that's what it would be. But that's only when all the sides are the same. Most of what we're going to look at here is when two sides are the same, your traditional isosceles triangle. All right, so that little recap they say right here, isosceles triangles have two sides, at least two sides of equal length. You can see it right here. These markings tell you that you've got two sides that are equal. Okay, so just to go over some important vocabulary now for isosceles triangles. The angle that's determined by or created by the congruent sides. So here's your congruent sides, the place that they meet. They don't meet out here. The place that the two congruent sides meet, this third side is not congruent in this picture, just these two. The place where they meet, that's going to be called your vertex. The angle formed is your vertex angle. The side that's opposite that angle, when they say opposite, they mean across the shape. That's going to be called your base. And then the two angles that are formed down there are your base angles. So you have two equal sides. That's what makes it isosceles. Where they meet is your vertex angle. And what ends up happening, we're going to get into this, is it creates two angles down here, the base angles that are equal, and a third angle at the vertex, which if I only have two equal sides, will not equal these two angles. Okay, so there's your vocabulary, your base, your two congruent sides, and your vertex. All right, so the first theorem we're going to take a look at here is called your isosceles triangle symmetry theorem. So the line containing the bisector of the vertex angle. So if we know that this side equals this side, and this is an isosceles triangle, the bisector of this angle is going to give symmetry to this triangle, meaning both sides are going to be a reflection across this line. So that's true for all isosceles triangles. If I cut them straight down, bisect the vertex angle, that's going to give that triangle some symmetry, or I could reflect over that line. So recall that in a triangle, the segment from a vertex perpendicular to the line containing the opposite side is called the altitude of the triangle. Now it says recall that. That's not something we've necessarily covered. So let's talk about what that looks like. This, in this case, would be the altitude. It goes from the vertex here to the opposite side, and it's going to be 90 degrees to the other side. That's going to be called the altitude. But this is our nice, perfect little triangle. What if we have a triangle that's not perfect? Like this. This is just a scalene triangle. The altitude would go from this point up here, 90 degrees, to the other side. Okay, so the segment from a vertex, all of these could be a vertex. Okay, from a vertex to the opposite side, 90 degrees, that's going to be called the altitude, which is like the height. That's the height of the triangle. The segment that's connecting a vertex of the triangle to the midpoint of the opposite side. So notice, because I drew this triangle very much in a scalene fashion where none of the sides are equal, there's nothing special about it. The altitude here did not hit the midpoint. The midpoint would be somewhere over here that splits this side. So I'm going to again draw a triangle that looks a little different here on purpose. If I've got this triangle and I want to draw the median, that's the segment connecting a vertex. So I'm going to go from here to the midpoint of the opposite side. So midpoint of this side looks to be somewhere over here. I can show that by putting markings to show that these two pieces now are equal. That makes that the midpoint. And the line that goes from the vertex to that, it'll be a straight line. It is not going to hit at 90 degrees necessarily, but if it goes from a vertex to the midpoint, that's going to be called a median. Now, what's special about isosceles triangles is when we go from that vertex angle, okay, to the midpoint on the other side, it also hits at 90 degrees. It's the perpendicular bisector of that side. So this is both the altitude and the median. So that's just something special about isosceles triangles. That line is the same thing. Over here, the median would go like this over here somewhere to find that midpoint. So the median and the altitude, if I drop the altitude here straight down 90 degrees, in most triangles, the median and the altitude are two different line segments. But in our isosceles triangle, the line that bisects the vertex angle, it's going to be the altitude. It's going to hit the other side at 90 degrees. And it's going to be the median. It's going to hit this and split it into two equal pieces, meaning it hits the midpoint. All right. A couple theorems here real quick. We already kind of hit on some of them. In an isosceles triangle, the bisector of the vertex angle, the perpendicular bisector of the base, and the median to the base are the same line, and that's what we just showed. This line right here is the bisector of the vertex angle. It's the perpendicular bisector of the base. It's cutting this into two equal pieces. It's hitting it at 90 degrees, perpendicular bisector. And it's the median to the base, of course. If it's bisecting it, it's hitting the midpoint, which makes it the median to the base. So that's what's special about an isosceles triangle in terms of the altitude, the median, and the bisector of the vertex angle. Now, I already touched on these two already as well. If two sides of a triangle are congruent, it's an isosceles triangle. But more than that, we know that the angles opposite those sides are congruent. So you can see in the picture, you've got your two sides. Remember, you've got your vertex up top. The two base angles are equal. So as soon as you see two congruent sides, you know there's two congruent angles. That's your triangle base angles theorem. And the converse of this is true as well. If you have two angles in a triangle that are congruent to each other, we automatically know the sides opposite them. So across is what we're talking about, opposite and opposite. That's why those two sides are equal, not any other two sides. The two sides that are opposite those equal angles are also equal. So we can be given the angles, we know the sides are congruent. We can be given the sides and know that the angles are congruent. All right, let's try some problems now using that information that we've got. I'm going to zoom you in here a little bit. Okay, example number 1. Pi equals or is congruent to PT. We can see that it's already marked. And that's also equal to PS. And again, we can see that in the picture, it's already marked. Now, TP, this line right here, bisects triangle or angle ITS. So this big angle here is being cut into two equal pieces. So I'm going to show that by putting those two little loops here. I know this angle equals this angle because TP is bisecting this big angle ITS. And now they tell me that ITS, that whole thing, is 148. So if it's being bisected, it's being cut into two equal pieces. If I cut 148 into two equal pieces, that's 74. So I know both of these are 74 because this big angle ITS is 148. TP is bisecting it, cutting it into two equal pieces, so they are both 74. Now, with all that information, they want me to determine the measure of angle IPT. So they're looking for this angle right here. Just with the information that I've got, I can figure that out based on my isosceles triangle base angles theorem. Two sides are equal, so two angles are equal. So looking at this picture, two sides of this triangle are equal, so the two base angles are equal. So this angle is also going to equal 74. That would be true over here as well, but that's not going to help us in solving for this angle right here. We're going to work inside this triangle. We know that the three angles of a triangle equal 180. I've already got two of them, so just subtract these from 180 and you'll have your missing angle. So we're going to minus 74 twice, or you could put them together and it would be 148 that you're subtracting from 180. And that ends up equaling 32 degrees. So the measure of IPT is 32 degrees. Okay, let's slide over. Example number 2. Here's what's given to us, and all of it is represented in the picture. MQ is congruent to MT. MQ, MT, you see those markings, that's what that means, they're congruent. MY is perpendicular to or hits at 90 degrees, QT. Here's QT, here's MY. The 90 degrees right there tells you they're perpendicular. So we could look at this picture without the given and know everything, but it kind of gives it to you twice, once in the picture and then once in the given. And then QMY is equal to 18. We can see that. We want to determine the angle of angle T. Okay, so what we know is special about an isosceles triangle, and since this side equals this side, I know this is isosceles. There's a couple things that I know. I know that these two angles over here are going to be equal to each other. I also know that if this line is going from the vertex, hits the base at 90 degrees, based on this up here, the bisector of the vertex is the perpendicular bisector of the base. So because I see this is hitting at 90 degrees, I know that this line is the bisector of the vertex. So if this little one's 18, this little one is also 18. If this wasn't an isosceles triangle, then I don't necessarily know all that. But this is what's true about an isosceles triangle. Now I'm trying to find angle T over here. All I've got right now is that this angle is 18. But if this is 90, these are a linear pair. This is going to have to be 90 as well because they're going to have to add up to 180, 90 plus 90. Well, now I have 2 out of 3 angles. So I know they're going to have to add up to 180. So 180 minus 90 minus 18 will leave me 72. So this angle has to be 72. The measure of angle T is 72 degrees. All right, let's flip it over. All right, example 2 is done here for you. We're going to use example 2 to try and fill out our own proof here in a second. So let's make sure we understand what's going on in this proof. So the figure at the right, AB is congruent to AC, that's marked. What's not marked is that angle 1 equals angle 2. I'm going to mark it. Angle 1 equals angle 2. We want to prove that this line right here, BC, is parallel to this line. And we know to prove that, we have to show that corresponding angles or alternate interior angles or alternate exterior angles are congruent. If we can show that corresponding angles are congruent or alternate interior, alternate exterior are congruent, we can prove that those lines are parallel. So we have these angles here. If you look at 1 and 3, those are corresponding angles when you take this line and use it as the transversal, right? Bottom left, bottom left. So if I can prove that angles 1 and 3 are equal to each other, corresponding angles being equal means these must be parallel. So that's what this proof kind of walks through. So first you state what's given. When I do these, I like to just put all of the given. You notice how they did 2 separate lines for the given. They're splitting it up, showing I'm going to use this here and then I'm going to use this here. You can plug it all in, so you'd only have 4 lines instead of 5. You can just shove it all in there and call it given. That's perfectly fine. So first thing they're going to do is state that these two sides are equal. Now they can state that angle 2 equals angle 3. So this angle has to equal this angle. Okay, because that's the isosceles triangle base angles theorem. you have two equal sides. The two angles opposite those sides must be equal based on the isosceles triangle base angles theorem. So 2 and 3 are equal. Well, 1 and 2 are equal. That was given to us. And so if you look at these last two lines, we've used angle 2 twice. It's congruent to 3. It's congruent to 1, which means these two are also congruent to each other. That's your transitive property. And therefore, once we've proven that angle 1 and angle 3 are congruent to each other, we are now allowed to state that those two lines must be parallel because corresponding angles are congruent. All right, let's try now our own. We're going to write a proof here. So we need our conclusions. I'm just going to make this nice and big. And our justifications. All right, the first thing you should do is just state what you've got, and I'm going to put it all in there. So everything that was given to us. AD is congruent to AE. If you take a look at the picture that's marked for you, these markings tell you AD is congruent to AE. And then angle D is congruent to angle B. And that's all just part of my given. And that second part, angle D and B, you can see they are congruent right here. So our last line is going to prove this line is parallel to this line. So again, we've kind of got to use these transversals and alternate interior, corresponding, stuff like that. Right now, these two are not any of those special angles because they're not touching the same transversal. Angle D is part of this transversal. It's relating to angle C as alternate interior. And this angle is measuring out with this one. Okay, and those would be alternate interior. So looking ahead, if I can prove that angle E is equal to angle B, I can prove that these two lines are parallel to each other because alternate interior angles, if you count this as your transversal, are equal to each other. Okay, so the way I'm going to do that is I'm going to use the fact that this is an isosceles triangle that lets me know that these two angles must be equal to each other. If D is equal to E, well, then E must also be equal to B because these two are equal to each other. We're going to use the transitive property to get there. So first thing we're going to do is show that these two are equal because it's an isosceles triangle. Okay, and then we're going to use the transitive property to show that these two are equal to each other. And once we know this equals this, because of your alternate interior angles, we can prove that these are parallel. Okay, so I just kind of ran out the steps there. Let's put them in the proof. So number 2, I can say that angle D equals, or is congruent to, I should say. I don't have the exact measurements, right? So I can't say equals, but I know it's congruent to angle E, and that's based off that theorem on the other side. I have two equal sides, so I know there's two equal angles. You can find that one right here. Two equal sides, so I know there's two equal angles. So this is your isosceles triangle base angles theorem. I'm going to use a triangle symbol. Base angle theorem. All right, so I'm allowed to conclude or deduce that these two are equal because I see an isosceles triangle. Now, if I look at my last two lines, I have D congruent to E and I have D congruent to B. That means they're congruent to each other, so I'm going to go ahead and write that. Angle B down here must be congruent to angle E, and that's the transitive property. And now that I know that B and E are equal to each other, I can prove that these two are parallel. So remember, your last line is always what you're trying to prove. So DE is parallel to BC because alternate interior angles are congruent. And I could have even abbreviated that with my congruent there. So as we go through these two, for like step 2, the isosceles triangle base angles theorem, like if you're worried about getting that exactly right, you don't need to worry about it too much. You could even use the symbols like this to show, hey, I had an isosceles triangle that had 2 equal sides. Therefore, I know I have an isosceles triangle that has 2 equal angles. Okay, that's good enough. And same thing here. There was an exact theorem here. We don't have to worry about trying to flip through all our notes to find that exact wording. We know these are parallel because alternate interior angles are congruent. That's good enough. All right, and one last thing we want to look at here in this section, we've got these 2 unequal sides and angles theorem. All right, so what happens when we're looking at triangles that may not be isosceles? They have unequal sides. What do they tell us about the angles, or if we're given the angles and they're not equal to each other, what does that tell us about the sides? So it says if the 2 sides of a triangle are not congruent, then the angles opposite them are also not congruent. So just like we know when we have an isosceles triangle, 2 equal sides make 2 equal angles. Well, 2 sides that are not equal make 2 angles that are not equal. But here's the key part here. The larger angle is opposite the larger side. So if I've got a triangle, and let's say this side is 5 and this side is 7. Okay, they are not going to create equal angles. And as I compare the angles that are opposite from these, so opposite from 7 would be this angle. And the reason I'm looking at that angle is because if you look at the 2 sides of that angle, they are opening up and creating this side. If I squeeze this angle down and make it narrower, now I've made this side less than 7. Okay, so the fact that this angle is what it is making this side 7. So if I look at the angle that's across from 5, if it's only making 5 and this one's making 7, we know that this angle is the larger angle compared to this one because the side that's opposite this angle is smaller than the side that's opposite this angle. So that's what this theorem says. And then we can also look at the angles first and then figure stuff out about the sides. So if 2 angles of a triangle are not congruent, we have 2 angles. So let's say this one is 90 degrees and this one is 45 degrees. Okay, 2 angles that are not equal. The sides opposite them are not congruent. So that side and this side are not congruent because they're opposite different angles. And the longer side is opposite the longer angle. So I know that this side over here is going to be larger than this side over here. This will be smaller. Okay, because it's across from the smaller angle. Notice I don't know much about the other side because I don't have this angle, but this is 90 and this is 45. I can figure out what this angle is because they have to add up to 180. So this would be 45, and actually, so now the side across from this 45 would equal the side across from this 45. So in this case, I know this is 45 degrees because if I take these from 180, that's what I get. So this side over here is going to equal this one. So it's also going to be smaller than the 90. So this one's larger than these. But I can go ahead and put markings on this side and this side. They must be equal to each other because this is an isosceles triangle. All right, down here. Scalene triangle, we're talking about the big one out here, MNO. Scalene means all the sides are not equal to each other. They tell you that MO is bigger than MN. And then they tell you that MN, it's open towards MN, is larger than NO. So based on all of that, this one's bigger than this one, but this one's bigger than this one. So here's the largest. This one is in the middle. And this one out here is the smallest. List the angles in the triangle from least to greatest. Okay, so from least to greatest, the smallest angle is going to be across from the smallest side. So my smallest side is here. You go across the shape. Angle M is going to be the smallest. We're going from least to greatest. The biggest angle is going to be across from the largest side. So n is the largest. So if we're going from least to greatest, the next angle in this triangle would be O. And then again, the largest angle is across from the largest side. And so that is n. Okay. Last one here. Triangle PQR. I'm given these measurements and I want to figure out what's the shortest side of this triangle. So I'm going to sketch this out real quick. Not drawn to scale because, like, look, this kind of looks like a 90. It's not necessarily 90 degrees. I'm just drawing a triangle here. We'll just go PQR, doesn't matter. P is 72. R is 53. We want to find out the shortest side. So just comparing these two angles, this angle tells me about QR and this angle tells me about PQ. Clearly PQ is going to be smaller than QR because it's across from a smaller angle. But I better go double check what this angle is if I want to get the absolute shortest side of the entire triangle. So if I want to find that missing angle, it's 180 minus 72 minus 53. That's 55 degrees. So this angle is 55 degrees. So the shortest side will be across from the smallest angle. Smallest angle here is 53, which means the smallest side is opposite it or across from it. So the shortest side is this right here, PQ.